Welcome, everyone. Thanks for joining at this very late hour in the day for the last session. My name is Vipul. I'm a senior manager for EKS. My teams are responsible for all the different aspects of managing Kubernetes control planes. I've been working with Kubernetes since the 1.3 release, and I worked on OpenStack prior to that, so open source is kind of native to me. With me, I have Shyam, who's he's been working on Kubernetes for 6 years. He brings Kubernetes expertise to EKS, and he's also the co-chair of SIG Scalability upstream. And today, we're going to talk about how EKS operates Kubernetes at scale. We'll go deep into kind of some of the trade-offs that we make as we operate EKS on a daily basis. We want to give you a view into kind of some of the behind the curtains things that we do to be able to, manage hundreds of thousands of clusters for our customers. Finally, we realize that we're standing between you and going to the hundreds of parties that are going on right now. So we're going to try to keep this, somewhat short, hopefully, and hopefully it'll be useful for you guys as well. So before we go into Kubernetes, I want to highlight a statistic that came from the CNCF, and it speaks to how important Kubernetes is to AWS. So 65% of Kubernetes users choose AWS to run their containers. Customers also choose to run not just on EKS, but we have lots of customers that are running self-managed Kubernetes on AWS. So that fact is actually very important to us because it drives how we think about improving Kubernetes. It's not just for EKS, but it's for any AWS user. So what is Amazon EKS? EKS is a managed service that provides the flexibility of Kubernetes with the security and resiliency of AWS managed service. So some of the guiding principles for EKS, it's fully upstream, it's certified, it's conformant. So technically, applications that run on open source Kubernetes, they should run on EKS just as well. EKS supports 4 versions of Kubernetes that gives customers time to perform upgrades, those kind of things. We also support versions that are beyond what upstream supports. So what that means is oftentimes there's important patches that EKS will backport to older versions. They could be security patches or bug fixes, those kind of things. EKS is a managed Kubernetes experience, so we effectively give you the security stability and the operational excellence of a AWS managed service. EKS reduces the complexity of operating Kubernetes. Our goal is to make it boring and simple as possible. Customers choose EKS because even though Kubernetes has actually done a good job of orchestrating containers and making that easier, managing Kubernetes actually is very, very difficult. It requires expertise. You got to, hire engineers. It requires a lot of, time doing upgrades, monitoring for, different types of failure modes, scaling the control plane. Also, applications that you deploy into the cluster, you have to manage the life cycle of those things along with the control plane itself. So all of this really is time that you're spending that's not providing value to your end user. So the EKS mission is to effectively provide the undifferentiated heavy lifting of securing and operating Kubernetes at scale. So let's talk about where EKS is available. So AWS Cloud spans 96 AZs, 30 regions. EKS is in most, if not all of these regions. What's more interesting, I think, is the scale at which we operate. So as of this year, EKS team operates hundreds of thousands of clusters in production worldwide. Customers are running different types of workloads on EKS. They all bring kind of unique scaling challenges for us, but we're kind of learning along the way based on what customers are doing with EKS. EKS has orchestrated millions of cluster updates, and this is both customer-driven updates as well as canaries that we run regularly to orchestrate kind of the workflows that we have. EKS has supported billions of compute hours attached as worker nodes. So what that tells us is Customers today are running mission-critical applications on EKS. So what are we going to talk about today? So essentially, this is our agenda. A couple of slides ago, we talked about undifferentiated heavy lifting. So what does undifferentiated heavy lifting mean to us? What do we obsess about on a daily basis in order to improve EKS? So this wheel, at its core, what we care about is all of these things that you see on this wheel. We call it our wheel of fortune. Sometimes, there's different spokes on this wheel that are at odds with one another. And, an example of that would be efficiency versus performance, right? We want to be able to run an efficient service, but also provide the best performance. So our job is to kind of look at all these things and figure out the right balance so that we're providing, the best experience for our customers. So some of these trade-offs that we have to make are pretty challenging. They require us to think hard about what decisions we're making for customers. And we're going to touch on each one of these kind of things throughout this presentation and also kind of take you behind the scenes as to how EKS has made various decisions along the way to keep this sort of circle balanced. So job zero for us is security. It starts with our architecture. So isolation is effectively a key tenet for EKS. Every cluster is logically isolated from any other cluster with private VPCs. Shyam is going to go kind of deeper into what that looks like. But in terms of security, we also think about supply chain. This ensures that Kubernetes, the software that we run within the Kubernetes cluster is always secure. We participate in the Kubernetes security working group, and where we have visibility into CVEs before they're even announced publicly. And so our goal is to automatically patch each one of our clusters around the world prior to any CV getting disclosed. We also discover new issues. We work with the upstream community to disclose these safely and also provide remediations for those issues. Compliance, EKS is fully compliant with most of the major standards, FedRAMP, PCI, HIPAA. What this really means for you is that it's everything, effectively it means that everything is patched, including the OS that we operate Kubernetes on top of. And finally, EKS gives you security controls, so in terms of who has access to your cluster, what sorts of auditing capabilities you have, Kubernetes audit logs, and we also provide recommendations. So oftentimes there's issues with CVEs or issues with Kubernetes that are not necessarily EKS, and oftentimes you have to go update your applications and those kind of things. So EKS is helping customers also navigate some of the things, not just control plane. We obsess about availability. We offer customers an 99.95% SLA. Again, this is not best effort, it's a guarantee. We measure our SLA. We continuously improve this. We invest in issues that we find that impact the SLA. A big part of why we're able to offer this SLA is the AZ redundant architecture that we have, and we're going to go a little bit deeper into that as well. And sometimes things are beyond, there's failure modes in Kubernetes that go beyond just a simple API server availabilities, things like webhooks that come into the play that can impact availability, and that's where kind of our support comes in, and we help customers navigate a lot of the webhook issues that they see that impact their APIs. Durability. So durability of data is a priority for us, right? So this is where etcd comes in. Etcd is probably the most critical part of managing your cluster. It's usually invisible to customers until something goes wrong. And it's also the most complex piece within a Kubernetes cluster to get right. So etcd is quorum-based. And when things are working, great. As long as you have quorum, things work great. If you're to lose quorum, if 2 out of 3 nodes, for example, are lost, now you have to go restore that cluster from some known state, and EKS takes some of this complexity away from you. So first, we take periodic backups. So all the data that's in etcd is effectively encrypted and backed up. We use this data for disaster recovery, or if bad things happen. So if you need to roll back some change that you made, and the best option is to restore from a backup. We're able to do those kind of things. We also use persistent volumes. This is where the data files for etcd live. This means that even if you lose quorum, all the data that belong to your cluster is not lost. So there's lots of other complexities when it comes to maintaining etcd. Specifically, there are issues around compaction, defrag. These things impact individual requests going to Kubernetes. And so EKS, our team is working with the upstream etcd community to kind of improve the impact those operations have to our customers. So reliability. So again, we talked about our goal is to make Kubernetes boring. We do this by focusing on reliability. So reliability is really about ensuring that the software running in your Kubernetes cluster is well tested, is functionally correct, and it continues to improve as we encounter new failure modes. So we start with how we qualify new versions. Each new version of Kubernetes goes through different testing phases that include conformance testing, scale testing, and feature-level regression testing. We leverage upstream tests where we can, but we also have EKS-specific tests where we need them. So our customers are also teaching us different ways Kubernetes fail. Some of these learnings are unique because of the scale at which customers or we are operating. Sometimes they're actually just bugs that the community hasn't caught. So all these learnings have allowed us to effectively make changes back up to the community and have those be available for everybody, not just AWS customers. And finally, our mechanisms around like how we obsess about failures and drive corrective actions, they hold us accountable in terms of making sure that the same failure doesn't happen again. Scalability. So a key aspect of scalability for us is to meet where the customer is at. So we have customers that want to do very large clusters. We have customers that want to do many small clusters. What we want to do as EKS is to be able to provide a service that can work for different use cases. So one of the things that we're focused on is pushing boundaries. So we're taking various scale tests that exist upstream, tests that we've developed, and trying to figure out, okay, what's the next bottleneck that we need to go resolve. Over the past year, we've resolved various issues in the VPC CNI plugin that we have. We've resolved issues in the EC2 APIs. We've resolved issues in Cluster Autoscaler. All these things are kind of discovered through the testing we do to push some of these boundaries. We work with SIG Scalability upstream to improve the testing that they have upstream, as well as take that testing and run it internally. Finally, one of our goals is to, upstream Kubernetes runs 5,000 K-node tests today. So our goal is to be able to make that a bigger number and figure out what the bottlenecks exist as we do that. Performance. So you can build scalable systems that are performant. You can build scalable systems that are not performant, or performance systems that are not scalable. We're trying to focus on both. So we want to build scalable and performance systems. So we obsess about providing performance services that have well-defined SLOs. So effectively what that means is meaningful work is done within some reasonable amount of time. And so examples of this would be pod startup times, API latencies. So we measure these SLOs, we review them regularly, and we try to improve them continuously. Sometimes this requires us to work on improvements that not only benefit AWS, but also any Kubernetes user. So one example is a recent change that we made to change the gzip compression ratio. And what ended up happening was we were able to reduce list latencies by 60% for all Kubernetes users. Efficiency. So what we're finding is our customers are using EKS for various different types of workloads. So some customers are running batch jobs that are very high throughput. Others are just running static set of applications. These workloads have a different sort of demand from the cluster. So what this does is gives us an opportunity to optimize kind of our fleet of clusters more efficiently. So we do this by right sizing based on what the workload demand is. So clusters that have less API requests or lower mutations. We're able to run them in smaller instances, whereas the batch type workloads may require larger instances. So the trade-off here is making sure that we're not compromising availability for any efficiency gains that we're getting. The end goal being we want to reduce the cost to run EKS, but also pass that cost back down to you. So with that, I'm going to hand it over to Shyam. He's going to go deeper into kind of all these different areas we talked about, and also open up the curtains a bit so that you know what's going on and how we run EKS.
All right. Thanks, Vipul. So they say successful services make infrastructure and operations boring for their customers. And if you frequented cloud computing conferences like this one, you would have heard this phrase a lot. And Vipul himself said this twice. But there's a lot of innovations that actually go in behind the scenes to make it boring. And at EKS, we are continually pushing the edge and driving innovations that make both our customers and our lives a bit more boring with each passing day. Let's dive into some of the innovations we made this year. We'll talk about those a bit in detail and also some of the exciting ones that are coming up over the course of the next few months. So quick background. This is how the EKS control plane, the cluster control plane, looks like at a high level. There's like Vipul mentioned, it's a single tenant model where each cluster control plane is placed within its own dedicated VPC, which is isolated from other clusters, right? So this provides for better security guarantees. And we manage a highly available setup. And what that means is the access, we always try to make sure that the access to the Kubernetes API endpoint is up and running. And one of the things we do there is AZ redundancy. As you can see, a lot of the components there are replicated across multiple AZs. So if one AZ goes down, the others can quickly pick up. And it's also resistant to single component failures in any one of those instances. And besides this, we do a bunch of other stuff as well. We continuously monitor the instances, their usage, and seamlessly scale them up and down, the instance types, CPU, memory, and stuff like that based on customer workloads. And we manage the lifecycle of etcd, which is the set of instances in the bottom row, which is the backend database, making sure that we take care of all its lifecycle actions, such as provisioning, right-sizing, backups, defrag, and so on. And finally, all these instances run a whole lot of software, and it's Kubernetes software, etcd software, and a bunch of EKS components added on top of that, which we need to keep up to date with newer Kubernetes versions, releases, and security fixes, bug fixes, and so on. All right. So let's start with zonal redundancy. This is an abstraction of the previous diagram that focuses on the core control plane components and their communication. As you can see, all the components are replicated right across AZs, and their communication is also replicated across AZs. These AZs are a little bit like neighbors. When life's going good, they're talking to each other, they're communicating well, they have each other's backs. But sometimes an availability zone runs into a failure, and when that happens, the communication may be disrupted in that zone, or some of the functionality in that zone may not be functioning perfectly. It's a bit like that potluck where AZ2 and AZ3 had, but they forgot to invite AZ1. So now AZ1 wouldn't talk to AZ2 or 3, or it'll just talk less. So eventually, in such cases, when this happens in cloud services, the AZ recovers, right? AZ1 will eventually recover, it'll come around and talk to these other two AZs. But in the meanwhile, AZ2 and AZ3 need to shoulder a bunch of additional responsibilities in order to make sure that smooth operations are carried out, right? So, like, pick up the kids from their piano lessons, or push the trash cans forward and stuff. But what happens when some of the components in the AZ are communicating with the components in the other AZs, but some don't? Or let's say the components are able to talk to the other AZ, but they're not able to do this perfectly with, let's say, increased latencies, reduced throughput, stuff like that. Which brings us to this next issue, that AZ failure modes, they're really weird. Their effects manifest in many different ways, right? So like I was saying, there's a lot of variance in how they can affect the different components. For instance, let's say an AZ was completely down in case there's a fire in a data center, right? We try really hard that our data centers don't catch fire, but that's life, and things like that happen. Or there may be a less invasive failure modes, like let's say there's a fiber cut between an AZ and its peer AZs, which causes reduced throughput between these AZs, or like higher latencies. And AWS has gathered tremendous experience here running cloud scale services over a decade, that it has meticulously and continually monitored, dissected, and analyzed these kind of AZ events. And using those learnings, we are currently working on a set of problems that are aimed at providing a holistic and deterministic AZ resiliency experience on the EKS control plane. And what does that mean? So no matter what kind of failure that the AZ is running into, we want to guarantee a very specific outcome to our customers all the time. And that is a seamless API, a Kubernetes API experience, which is not just about uptime, but it also covers more deeper aspects of customer experience, such as performance, right? Latencies and throughput of API requests. They continue to work well, and there are no errors, and so on. And the other thing is, we also don't want any disruption or delays in the Kubernetes controller workflows, because they are also something we promise to customers and we manage on behalf for customers. So we want to have this experience. Essentially, what we are doing is we are building on top of the AZ redundancy we are already offering today. That's based on component health checks, but we're going much deeper into the end user experience here, right? And this includes actions like moving the HCD leader from the bad AZ, if the leader is in a bad AZ, to a good AZ, so that it doesn't affect reads and writes to, like, database reads and write operations. And the other one is we want to make sure that all the leader-elected controllers in Kubernetes, like kube scheduler, kube controller manager, and certificates controller, for example, they all move to the good AZ, which guarantees that they won't run into any issues. Similarly, we also want to move all the traffic in the unhealthy AZ, from the unhealthy AZ to the healthy AZ. And this includes not just the CRUD, or like the create, read, update, delete API calls, but also long-running requests like watches and exec, proxy, port forward. These are all APIs that Kubernetes offers. All right, so while I was talking about the previous slide that we want to move all the workloads and controller workflows to the other instance, some of you might have had this question in your mind that, does this mean that, like, the other AZs have enough capacity to be able to handle all this extra burden that's coming over from the unhealthy AZ? And yes, the answer is yes. We over-provision the instances across these AZs with respect to the CPU, memory, and network bandwidth, and that kind of capacity to be able to handle all the traffic without one full AZ. And this brings us to some interesting challenges around how we manage the scaling of the control plane and the performance around it. So, all right, so this is a slide actually that I picked up from my reInvent talk in 2021, which explains about control plane right sizing that EKS does. This has been there for close to 2 years now. It's a system that automatically scales the instances of the AP7 HCD up and down based on various signals, usage signals such as CPU, memory usage, and cluster size, which is the number of nodes that are in the customer's cluster. But we did not stop there. I did promise back then that we were going to have some exciting launches going forward. And what we did is we've analyzed our whole fleet over the course of an year and drawn some insights that tell us, that gave us some more signals and some more dimensions on which we should scale to actually make this really delightful for the customer. So what did we do? These are all the improvements. I'm really proud of what the team has achieved here on these fronts. So firstly, we added a bunch of newer signals. One of them is the HCD database size, which roughly corresponds to the activity that's going on in the cluster, as well as the number of objects in your cluster, which roughly corresponds to the scale of your workloads. Right? We're using the HCD database size to scale up proactively, even before CPU memory usage goes up high. Similarly, the other one is HCD range requests. These are nothing but, it's basically list requests where you're trying to get not one object, but a large number of objects. And we've seen the signal that when customers send a lot of these list requests, or there's a spike in them, that means there's going to be some activity that's going to come up soon in the cluster. So we're also using that as another signal. And in terms of what do we actually scale, right? What are the dimensions? We already spoke about the instance type with respect to CPU, memory, and so on. But we've added a bunch of more dimensions, and this is going a little bit into the software. Previously, we scaled the infrastructure, and now we're also scaling the software that needs to support customers' higher scales. And a few examples of that are the Kubernetes controller manager, QPS and burst limits, the kube schedulers, QPS. These are components that go into creating pods behind your deployments and scheduling them to nodes and stuff. And similarly, we're now excited to announce support for 100,000 secrets with KMS encryption. So that's a big number. And previously, we used to support only 10,000. So yeah, that combined with we've also improved our scaling algorithm and some of the logic that goes behind making these scaling decisions to respond faster and more proactively, right? One big thing we did here is scaling updates, which previously used to take close to 30 to 40 minutes. We brought them down to 10 minutes, so they happen much quicker. API server and HCD also are able to scale now in parallel, and we've leveraged this to also proactively scale the control plane. So let's say API server is having higher usage, we scale up, but we also scale HCD in parallel just to be sure in case the utilization goes up, right? So what has all this given us? We are now able to support our customers to scale their clusters seamlessly to 5,000 node clusters without needing any pre-scaling. So if any of you have used EKS before, you might have heard about this method we have for customers who expect to have a huge spike in their pods and like in their workloads. They come to us with pre-scaling requests to take care of that. Now we no longer need to do that. This is all taken care of with EKS. And coming up next, this is a new thing we are building, and expect that to come sometime in early 2023, which is the horizontal scaling of API servers. So we spoke about changing instance types up and down, right, which is vertical scaling. And we are appending to that horizontal scaling of API server instances, depending on your cluster size. We'll dynamically add and remove more API server instances. This is one of the key benefits of the architecture we have today in EKS, that we decouple HCD and API server. So HCD is stateless, HCD is stateful, API server is stateless. So we are able to use that to horizontally scale. And this helps provide better traffic split especially at larger scales, when there are, let's say, watch requests or a large number of long-running connections, or in general, just more workload. And the other aspect is failover. Failover is, let's say, instead of 2 instances, when you have 4 instances, you have a much better failover scenario. Let's say when one instance goes down, only 25% of the traffic has to move to the other 3 instances, as opposed to with lesser number of instances. All right, so how are we doing all this? How are we able to more aggressively scale up, horizontally scale up, use more capacities, and still keep the costs low for our customers. The way we do it is by doing the due diligence of continually experimenting and improving our utilization rates. We're trying to get down to the last drop, get the last drop of performance from our CPUs and so on and so forth. Some examples here that we've done in the last year is we've optimized memory allocations both within HCD and some of the components that run on the API server instances. We've tuned the GC, which is the garbage collection in Go, to kind of trade off CPU and memory in the right way. And the other example, which Vipul already talked about, is gzip compression. Gzip compression it happens as part of the Kubernetes API, and we made some improvements there on latencies and utilizations. Okay, switching gears a little bit now, I want to talk about HCD. HCD is it's the heart of the Kubernetes cluster. It's the backing database which stores all the state of your cluster, right? And it's based on this Raft consensus protocol, which essentially implements a strongly consistent and distributed log replication of transactions in your cluster. And it's the way Raft works. It works based off of this concept called quorum, which some of you may have heard already, which says that if the majority of number of instances in the cluster are up, then it will continue to operate seamlessly. So we run HCD in a 3-node mode, so that means majority is 2. So we are able to take a single node complete failure as well for our clusters, right? And just like API server, we are also right-sizing HCD instances for availability. And one of the things we take care of for making sure the data doesn't get lost and is durable is we periodically perform backups on the HCD instances. So this is again a recap from my last year's talk, which is about how we improved the load balancing between the API server and HCD. So API server talks to HCD. Here you can see it's talking directly. Previously, we used to have a load balancer, an L7 load balancer in between that did the job. So we got rid of that. It gave us some amazing wins in terms of performance because now it's directly network interface to network interface, no extra hop in between. It gave us better load balancing because let's say the API server instance in zone 1 is unable to talk to the HCD instance in zone 1 because it's, let's say, unhealthy, then it is able to load balance and even failover to the other instances, which is a great availability win for us. All right, so we took this a notch further with the introduction of static IPs for HCDs. What this does is, so we have these 3 HCD instances, right? And each of them have some IP. We now attach an additional IP to these instances, which are static. And what we mean by that is their lifetime. Those IPs live across instance lifetime. So there's one IP in each AZ. And let's say one of the instances goes down, then a new instance will come up with that same IP. So you might be wondering why is this relevant, right? Because HCD is a detail we manage and hide from you as customers. But what this translates to in terms of customer experience is because of these static IPs, during cluster updates, the HCD instances, they do not have to do any control plane operations around membership changes, which means that a new instance may go up, and let's say a third instance, let's say one instance is replaced by a new instance, and in between another instance goes unhealthy. So if there is, for example, let's say a quorum loss, that's still fine because these instances can come up and talk to each other with the same identities. This does not need a restore from backup and like a brand new restart of the cluster. So that, and the other aspect is the API server instances. You saw previously talk to HCD, right? So API server is the client of HCD. And because these IPs of HCDs are now fixed, the API server no longer needs to do discovery, which was a problem before. So that's kind of one of the trade-off for the availability, the improved availability that we provide. The trade-off is the complexity in terms of discovery, which can take up to a few seconds, right? And during that time, one of the instances unavailable. So this improves that too with static IPs. And we complemented the static IPs, or we are currently working on this, and this is coming soon. We complemented it with static volumes. What does this mean? So Vipul mentioned the term persistent volumes are used for etcd. Persistent volumes are basically like, we're talking about EBS volumes, which are network-mounted volumes which can live outside of the instance's lifetime, right? You can remove a volume and reattach it to a different one. So previously, each instance had its own volume in etcd. So when an instance went down, a new instance would come up with a new volume, and then that instance had to sync all the existing data from the other two peers. And this, firstly, it increased the time to recovery, let's say when one instance goes down. And secondly, it's basically a lot of churn that's created during the updates, because when EKS does updates of our fleet of etcd clusters, there's a lot of EBS provisioning and deprovisioning, which was an inefficiency for us. And with this feature, now what's happening is you can lose quorum, but the volumes are still there. So let's say 2 of your instances are down, the volumes are still there, and the new ones will come up, we'll just pick it up from there. And because of static IPs, the cluster membership is also preserved. So now they're able to just start where the last instance stopped. So yeah. Okay, so switching gears a little bit here again. Till now, we focused on an individual cluster and some of the workflows and maintenance activities that we are doing within the cluster. Now we'll zoom out a bit and look at a fleet of clusters, because EKS as a service essentially manages lots of clusters, hundreds of thousands of clusters, right? And one of the critical problems or the critical challenges is software delivery. Delivering software to so many instances and so many clusters is not very easy, but it is something which is critical to earning trust with our customers, because it's essentially how we deliver value and innovations to customers through new features or operational improvements or security fixes and so on. A little bit of background on the service architecture here. So EKS, just like many other AWS services, is regional, and each region is further split into different cells, which are nothing but AWS accounts, and we distribute customer clusters into these cells. So the cellular architecture pattern is something that shouldn't come as a surprise to anyone who's worked with large-scale distributed systems before. The important thing to note is we limit the maximum number of clusters we place within a given cell. And that helps us reduce the blast radius of any issues, let's say a bad deployment, or let's say some rate limits that are happening at the account level, for example. Yeah, so we'll talk more about this. We'll talk more about, I think the other thing I wanted to talk about before diving deeper into our CI/CD and software delivery process is how the control plane looks like inside, right? So previously we just looked at the instances and the infrastructure, but within them, there's a bunch of software running. There are tens of components, and these are not just Kubernetes components, but we're also adding a slew of EKS components on top of that to implement AWS integrations and features like IAM authentication or encryption, certificate issuance, monitoring, logging, and so on. Right, and a big challenge here is to ensure that all the software that we build is tested and distributed reliably, right, with so many moving pieces. And that's where testing comes in, and we're performing testing today at multiple dimensions. So one of the things is we test things at various levels of software packaging. For instance, each individual component that I showed previously gets tested separately, and then they get tested at the stage where all of them are collected together into a machine image or an army. And then we also test at the final stage, which is the cluster, all the pieces together end to end. And what do we actually test for? It's a broad portfolio of basic conformance tests, upgrade tests, scalability and performance tests, which on top of the upstream Kubernetes scale tests also measures our own EKS added components and their functionalities, right? And there's testing that also happens at different stages of deployment, like beta, gamma stage, and across every single prod stage. And even within that, we test across all regions to catch issues that are region specific or, yeah. And finally, we also continuously monitor. This is after we've already done the deployment. We continuously monitor our fleet across all the regions through long-running canaries, which mimic customer experience, right? And the goal of this is that they're designed to promptly catch any systemic issues, like, for example, a zonal failure or a bad deployment, which somehow fell through the cracks of all the previous testing. And a good example here is recently we observed an issue after one of our deployments that when the etcd instance was getting recycled, when the API server instance was getting recycled, the etcd instance was leaking connections in the underlying host's contract entries. And we actually caught this issue through our canaries, which do some aggressive updates and operations like that before customers ran into this issue, and we even fixed it before any of our customers ran into that. So, yeah. Platform version update. So you might be aware of this concept of platform versions if you've been through the EKS public documents. These are nothing but versions that are, for a given Kubernetes version, let's say you're on Kubernetes version 119, we keep releasing new features or updating the Kubernetes patch versions or maybe making security fixes and so on. And each time we do this, we release a new platform version and make it available to the customers through our public docs. And for these updates, again, it's a massive number of instances that we need to update. And these instances need different kinds of software updates, things like the Army, the Amazon machine images, the containers that are running on the control plane, as well as various other agents. And the tricky part here is how do we balance safety of this deployment with velocity? Because if you go too fast, there is a risk that an issue which comes up late into your deployment cycle has already been released to a lot of clusters, so there are blast radius concerns. But if you go too slow, then your velocity is hurt because you're taking more time to deliver features, bug fixes, and so on to customers. And one of the problems here was, like more than 6 months ago, I think these platform versions were slow. Especially, I'm talking about the total time it takes for EKS to deploy new platform versions to all the Kubernetes versions across all the regions in EKS, and that was taking close to 4 weeks. The reason was twofold. One is that a single cluster update took 40 to 45 minutes, and on top of that, there were some regional and cellular rate limits that we had to that we were bound to because of a bunch of dependency services. So what we did was we solved both those problems. One of the things we did was the single cluster update time. We reduced the average time from 40 minutes to less than 10 minutes. I think it's close to something like 8 to 9 minutes now. This was a tremendous win, and this includes various update types, not just version updates, but also a bunch of other customer-facing update types like OIDC provider association and encryption updates and so on. How did we make these improvements? There's a whole blog post around this where this is discussed on the EKS in the EKS homepage. But just to quickly go through some of the key improvements we did there was the concurrent API server and etcd updates, which I briefly mentioned before. And on top of that, we also switched to a blue-green style API server update, where instead of replacing one instance each time, one instance at a time, we bring up 2 new instances in parallel We drain this, we move the traffic over to the other two new instances, and we bring down the old ones. So that improved the speed as well. And we made some improvements in the API server, the instance bootstrap time by optimizing calls to S3 that previously used to lazily happen during runtime by prefetching blocks of binaries and large files ahead. Also, HCD warm-up time, we reduced it by using better health checks instead of relying on a fixed amount of time to initialize when a new instance comes up. And static volumes also helps here, because when a new instance comes up, there's not much work it has to do except catch up from when the last instance died. All right, so the single cluster update time combined with some innovations to AWS other services I was previously saying were our dependencies, like the network load balancer and the Amazon Route 53. These are services that recently made a bunch of improvements that increase the throughput they can support regionally, as well as the latencies of various operations like health checks and target registrations and deregistrations. Using all this, we brought down our global fleet patch time from 4 weeks to it's less than 10 days now, which is almost 4 times faster time to release any new software and bug fixes and so on. But one of the things is we're less than 10 days. We're really happy about it, but we're not ending there. We want to get better. And the reason why it's still so huge is because at the end, you're taking all these clusters and you're actually rotating a bunch of infrastructure. You're creating new instances, you're moving traffic over, you're registering targets, and so on. So this is, and security is P0 for us, right? Like, let's say when there's a critical security issue, we don't want to wait for still 8 days to actually roll out fixes to them while the issue is still under embargo, right? We want to do it at a much accelerated pace. And for that, we have another mechanism called in-place container updates, through which we, in a very targeted way, we replace containers on instances that are on already running instances without bouncing them off. So, yeah. We'll take over.
Cool. Thank you, Shyam. I hope that was insightful for all of you. So if you want to learn, if you're using Kubernetes or you're thinking about using Kubernetes and you want to learn more, there's a lot of docs that we have for getting started. And if you're already a EKS user, I highly recommend looking at the best practices guide, because we actually talk about how to configure workloads in your cluster to be highly available and those kind of things. And then we also have a public roadmap. So if you go to this site, you'll see what other customers are requesting from us, what they're talking about in terms of different implementation details that they want to see, or if you just want to have us go work on something that you think is important, this is a great place to add that. The number one thing is we want to build things, as you guys know, that are focused on what the customers want, and so this is like a great mechanism for you to give us that information. And then finally, so there's 2 more days left. There's a ton of sessions on and around EKS. So if you're interested in things like containers in general, or EKS, or how to more efficiently operate clusters, Carpenter is an example of that. There's sessions on on-prem Kubernetes. So yeah, feel free to go to these as well. And with that, that's all we have. Thank you.